Howdy. Howdy. Happy Monday. Welcome to the second lecture in the first year lecture program, the first year program's lecture series. The first one was, of course, by a professor of anthropology named Sheila Threya, who talked to us about dating human ancestry. Today's lecture is by my colleague and friend John Fackler, who's on faculty in chemistry. And before I introduce John, what I want to do is remind you that the third lecture is actually by a person who many consider to be the preeminent science fiction writer of our generation, whose name is Benford. Now, he's coming on November 6th, which actually coincides with the weekend that we beat the hell out of OU. And he's a Sooner, so we'll greet him appropriately when he gets here. But put that on your calendar. Monday, November 6th is Benford's lecture. John's been with the faculty at A&M for about 23 years. He came from Ohio or Indiana? Ohio. Went to school at Valparaiso, got his BS degree in 1956. Went on to MIT and got his PhD work, did his PhD work there, and then went to Berkeley, which is a small state school on the coast, and was bought out by Case Western Reserve in Ohio. He came to A&M in 1983 because he was wooed here to be the dean of the College of Science. He was a dean for 9 years, longer than any other dean had survived, and helped transform this place from an all-male, all-military academy to one of the top research programs in the nation. Right? John's here to talk to us a little bit about his research in common context. He's interested in gold, and so please help me introduce John Fackler.
Howdy. I hope you can hear me. I see my students in the front row. Don't giggle too much, gang. But it's certainly a pleasure to have you all come out in this very rainy day. I was here yesterday in the afternoon. We were here for a concert. And I hope some of you have an opportunity to attend concerts here periodically. The Brazos Valley Symphony Orchestra was here and it did a nice performance of Mahler's Symphony No. 1. This is what I'm interested in terms of chemistry, and I'm interested in more than just the chemistry of gold. There are a lot of very fascinating things about gold, and we'll tell you a little bit about them tonight. All of you are looking for this, obviously, someday, or many of you anyway. Hopefully we'll get it. But if you only have an 11-carat ring, be a little careful, because it's only got about 46% gold. And as a consequence, as you'll see, the gold could in fact deteriorate in the 25 years or 30 years or 40 years or 50 years that you might have your ring. I've talked to a number of old Aggies about how they can prevent their rings from deteriorating, and there are some very interesting ways, as we'll talk about. Of course, the element itself you see all around you. You like it for jewelry. Some of you certainly have gold jewelry of various sorts. Not many of you wear this type of gold jewelry, but it's certainly fascinating in some parts of the world. And there's certainly a lot of gold there. These are not light, I should point out. The element itself is only one of 81 non-radioactive fundamental components of nature itself. And that's very important. We'll look at some of its properties. First of all, it's element number 79 in this periodic table. There's a real table of the elements themselves. It exists over here. And right below it in the same column is an element that we haven't worked on yet, element 111. But presumably someday somebody will work with that element. It's a soft yellow metal, melting point over 1,000 degrees. Takes a lot of heat to do that. Has a very, very high boiling point. And it has some very interesting properties. First of all, it's not attacked by oxygen or sulfur. Kind of important. It's very heavy, very dense. You've perhaps noticed that. But it does react with chlorine and chlorine-generating solutions. Aqua regia is a very important one. That's a mixture of nitric acid and hydrochloric acid. And that is the reagent that is traditionally used to dissolve gold, and I'll talk about that in a minute. But the important point here is chlorine exists in a lot of dishwashing solutions. We use water that has a lot of chlorine in it. And if you have some sulfur-containing components in your skin, some amino acids, for example, that contain sulfur, and some chlorine in the water, your Aggie ring could be dangerously deteriorating. And so you have to watch that. And over the years, watch out how much dishwashing you do with your Aggie ring on. Take it off. It's a kind of a rare element. As you can see, it's only a small portion of the Earth's crust compared with the iron and aluminum elements that are much more available. But there are some very interesting points here. It's malleable. That means you can pound it and make it shaped into a lot of different things by hammering. And you can actually make very thin layers of gold. 1 ounce, not very much, can cover 300 square feet. You'll see a picture later on of a building that has that on it. 45 miles of wire diameter of hair from 1 ounce. Wow. Good thing. Gold's an interesting element. It's conducting too, and we need that for some of the processes that we deal with gold. But what is my business? My business is in the university. It's to discover. Professor Simonik mentioned that, to transmit. We do talk about publishing our work and to disseminate knowledge, and that's why you're here tonight. We're dealing with students. And this is from a president of that institution about 80 miles across the way when he was president at the University of Texas. But for me, it's always a thrilling experience to be able as a scientist to discover new knowledge. And I like to think about this quotation from George Pimentel, who was a faculty member at Berkeley many years ago. Confession is to sin as teaching is to research. There's no point of the one without the other. So this combination of research and quality teaching is really important, I think, to Texas A&M and the development of our programs. But of course, we're always looking for money, aren't we? Sometimes our research grants die on us. How do you dissolve gold? This is what a chemist's scheme of things is. We have to dissolve this gold. I mentioned aqua regia, and that's pictured here in this little cartoon from about the Egyptian sun god Horus, who's actually eating the gold. This is aqua regia, nitric acid, hydrochloric acid mixture. But the Chinese, many, many years ago, found out this solution will actually dissolve gold. A solution of potassium nitrate and acetic acid and iron sulfate in a bamboo tube. What's causing that to occur? Today, some of the companies that actually get gold for us, get it out of the ground, use a cyclic thiourea with some iron sulfate to dissolve the gold. But the common way of dissolving gold from poor ores is with cyanide. Cyanide attacks gold very, very strongly and is used in the leaching process. Some of you perhaps have been in the Colorado mountains and in fact have seen the process they use for leaching gold out of ores. This is what we use to do our chemistry. We start out with a gold coin, which has virtually no other element in it, 99.99% gold. It's a Canadian coin. And then we get students to cut it up. And I learn that my students are good chemists when they can take a gold coin and cut it up and dissolve it, do chemistry with it. Imagine. And we, from that gold, make molecules. And in fact, we were fortunate enough a number of years ago to make the first examples of a gold compound with 4 carbon atoms attached to it in a square arrangement. The first work that had been done with that sort of an arrangement produced a compound that explodes. These materials are stable. They can be put in the desk, or they can be used in the lab at Heldenfels. But in addition to the gold being unstable in this configuration, this compound, which is called an ylide, this portion of the molecule here, or here, is also relatively reactive. And in fact, normally you could never store such a species by itself, certainly not this one, and it's very difficult to store this one. And it reacts with carbonyl functions to form epoxides. And so we discovered that, in fact, you could put these in a bottle, determine their structure molecularly, and cause the rupture of the gold carbon bond to utilize this portion of the molecule to make epoxides. Well, what are we talking about in terms of size? I want to teach you a little bit about sizes. You all know the size of a bacterium, right? You've heard of E. coli. Everybody has over the last couple of weeks when we had the spinach scare. E. coli, pretty big actually compared with a virus. A virus is pictured to scale here, happens to be the polio virus. This virus, not another cartoon blown up, has on it antibodies. And they're a lot smaller than the virus, but they're still pretty big. And here's a picture now of that, the antibody attached to some proteins, globular proteins and amino acids, and finally we get down to the sizes that I showed you in that previous slide here of these molecules. And so with these new techniques we have today, we can determine precise structures of molecules that are that small in this region. Well, how do we do that? First of all, we have to find a perfect crystal. We call it a single crystal. Here's an example of one. And that crystal is subjected to X-rays. And those X-rays are scattered off of the electrons in the crystal. And in that scattering, they produce an image like this. What we do is put a crystal like this on a machine where we can rotate that crystal in all sorts of different angles, and we can rotate the detector. Well, what's the detector? Today, the detector is a simple CCD camera. And in fact, we can get those X-rays into this CCD camera. There's a phosphor in front of it so that it produces light, and get this type of pattern. With computers, this pattern, with all these different angles that we can rotate the crystal in, gives us a structure. And we can deduce then the detailed molecular structure of these distances that are only 10 to the minus 8 or so centimeters in length, 10 to the minus 10 meters in length. They're really very, very small distances that we're talking about. Out of this work, we can get a lot of interesting chemistry. And I want to tell you a little bit about this chemistry because it's kind of old and interesting. If you take this aqua regia solution of gold, which really is primarily this material, and you happen to make a mistake and want to neutralize this aqua regia with ammonium hydroxide, lo and behold, you get a precipitate that explodes on you. Fulminating gold. A brown material. It happens to be non-crystalline, but it explodes. You can get at it a number of different ways, as is indicated here. But the interesting thing about this particular material is that it was looked at back in 1680s as a material that could be a medicine, a medicinal component. People ate it. Taken inwardly, it causes sweat. The heat of the body volatilizes, drives it through the pores. But they didn't know why it worked, and some people thought it was not doing anything anyway. This is the earliest actual connection I've seen between gold compounds and real medicine. But it turns out that the ancients actually used gold for what they assumed was medicinal purposes many, many years before that. And perhaps the Chinese, in that cartoon I showed you of dissolving gold, also used it for medical purposes. But today we do have gold drugs, authentic gold drugs. Here's one that's very important. It can be taken orally. It's called Aranafin. It's used in the control of rheumatoid arthritis. Some people can take it, and it's very, very effective. In fact, it's the most effective of the reagents that one can take to control rheumatoid arthritis for those people who can handle it. But unfortunately, many people are allergic to it. And so allergenic reactions can and do occur with people. So gold has lost a lot of its popularity as a drug for arthritic control. There are other ones today. But for animals, there are diseases, autoimmune diseases, where these gold drugs are used very regularly to control the diseases in cats and dogs. But we don't know why yet. We don't know what it is about the gold drugs that really function the way they do, why they function the way they do. Here are a couple of examples of ideas. Oxygen is involved clearly in the surface cells, and so people think that the gold drugs do something with regard to oxygen destruction of cells. The excited state of oxygen is a singlet. Some of you know that from your freshman chemistry. Most of you know it's a triplet in its ground state, but it can go to a singlet, and that singlet is very active and can destroy cells. The gold can cause it to go back to its more stable form, the triplet form. And maybe some of you have learned about this particular component that's in cells, nitric oxide. It's kind of important. It was the chemical of the year back when, about 10 years ago? It was the chemical of the year. And it reacts, unfortunately, with a component of oxygen that comes off of hemoglobin called superoxide and forms a peroxynitrite, which is very reactive and can destroy cells. And so this is another possible problem in rheumatoid arthritis, which is controlled by the fact that gold will interact with the NO and can cause the O2NO species, the nitric oxide, to be destroyed itself. Well, that's enough little chemistry now, but gold is involved in drugs. It's being used more and more now for cancer chemotherapy, and some real good finds in this particular area. But it really began with the alchemists, these studies of gold compound, converting base metals to gold. And here's the kind of vessel that was used. We all use this now in Heldenfels, right? Hermetic vessels. We don't even know what they look like. Base metal to gold. Isaac Newton was an alchemist. You all think of him in your calculus class and then get angry, right? But he was a famous Cambridge scientist who was really an alchemist, and he in fact wanted to convert base metals into gold. We even had an Aggie that did this. One of our colleagues, a distinguished professor, he thought he could convert mercury into gold and got involved and published this sort of work, and it was picked up by the Houston newspaper that put this cartoon on the front page in 1992 approximately. Well, of course, he never really did convert mercury to gold, but he took money to try to do that. Some people thought he was right. It's interesting what the press will do today. And as you read this, you can see that even though it's farcical to think about that happening, there were individuals who supported the fact that this distinguished professor was carrying out a recipe that really worked, an alchemy recipe. And obviously it did not work. Here's an example of the kind of gold that appeared as late as 1716, formed by conversion of a base metal into gold. In ancient Egypt, it was the priests that controlled this alchemy. They were the ones they were the chemists of the day. But they also learned to use gold in many fascinating ways. You can see some of these artifacts in Egypt if you ever go there. It shows you that you can make a foil that will cover a chair or cover a chariot, or you can melt the gold at 1064 degrees and make a mold and put into that mold the gold and make statues of this sort. Fantastic when you think about this being done 3,000 years ago. If you ever get to Cairo and the the museum there in Cairo itself, you can see this particular statue, or it really is a sarcophagus of King Tut, and it's a huge piece of gold that's represented by his face here. And then he's buried in this type of a tomb. Notice this is about 3 feet across and very thick. Try to lift that. Impossible. Certainly impossible for me. But there's certainly a lot of beautiful ways in which gold was used to colorfully deal with the tombs that were involved with the pharaohs. So gold had to be found in this region of the biblical world. Most of it was down here near the Red Sea that Egypt used. There were also some down below off this slide. But there were other places in the Near East that were involved. For example, it was found that in the 8th century BC, the Hebrews, the Israelites, had gold. That would be in this region here. King Solomon certainly had a lot of it. 31,000 pounds of it, they say. That's a lot of it. And the first coins that were made out of gold were from this region here, the Lydia region. The first gold coins, 561 BC. So we've had that element around a long time. We've used it how? Well, we've largely used it to decorate ourselves, and we've used it for money. Here's an old coin, decoration that the Celtics used with gold, and some Roman jewelry. So it's been around a long time for purposes of decorating ourselves. I like the situation in Colombia. I was down there back in the 60s, and I learned at that time that gold in Colombia was, of course, very important. Spanish found out that gold existed there and came over to the Americas and got a lot of that gold. And the gold was actually shipped in this way back to Spain from Colombia. Initially, the gold in Colombia was obtained by dissolving the gold in mercury as an element. And it turns out the Spanish had much mercury available, so they could bring that mercury over. I'll tell you a bit about that in a minute. My first experience, though, led to the observation of pieces of artwork like this in the museum in Bogota. This is about 2 feet in size, huge piece of gold. This is what Bogota looked like, and this is the museum itself, and the places where gold was found in Colombia were in the hills. Fun to do that, and I hope some of you someday have an opportunity to travel as I've done as a chemist. Here are some of the items you see in that museum. They're all native items, pieces of gold. This one's about 2 feet across this way and 1.5 feet in this dimension. And a conch shell covered completely by gold obtained by pounding, and a vase about 2 feet in size. Beautiful, beautiful pieces of gold that were used by the ancients. But this is how it was initially obtained. Mercury, as you know, is a liquid. Mercury dissolves gold, and that's another thing you don't want to get on your Aggie ring, ever, because your Aggie ring will dissolve in the mercury. But even today, one can find gold and pan for it by using mercury. And I wouldn't do this if I were you, because mercury's a poison and can get into your body and cause you problems. But alluvial glacial type gold can be found in various places. And out west, of course, you've all seen pictures of the panning for gold. Some of you may have panned for gold. How many of you have panned for gold? Any opportunities? Yeah, a good bunch of you have. That's good. I certainly had a chance to do that in California when I was there. But this is where gold is found all over the world. It's certainly available virtually everywhere. A lot of it in Australia. Of course, we think about our gold mainly in South Africa, which is the country that really controls the price of gold. There's a lot of it in Russia, in the Ural Mountains. And so it's not an element that we're not going to have with us. We're going to have it around for a long time, but it's getting it that's the problem. Here's a mine in France, and out of this mine in France, one produces gold ingots like this, which can be purchased. They're available to us. Well, what does it take to purchase gold? Well, until 1973, gold was money, real money. It was controlled money in the sense that the price was controlled. 1973, well, that's before most of you were born, but it's not long before you were born. And it was in that year that a Texan, John Conley, with Richard Nixon, took us off the gold standard. And as a result of that, the price of gold is now market-driven. And this is an excellent book for those of you who would like to read about history and the development of power through gold. Bernstein wrote an excellent book in this area. But here's what the prices look like of gold historically. You know, as it was controlled here, it went up a little bit. The government decided to raise the price here, but it stayed and stayed and stayed until 1973. And then it went out of this world. And then it dropped back down, and it's oscillated, and now it's going up again. Whether it'll go all the way up to the highest point, we don't know for sure, but it's been over $500 an ounce recently, even as high as $600 an ounce not very long ago. So it's really pretty expensive. But it can drop, as you can see from these slides, because it's market-driven. Who's controlling the price? Well, those countries who have the most gold. And so certainly South Africa controls a lot of the price. We have a lot of gold in Fort Knox in Kentucky, and we could take it out of there and sell it to lower the price. If, just like the oil reserves for oil, we have a gold reserve in Fort Knox, and we could lower the price if we felt that, if our government felt that it needed to, but so far we haven't had to do that. Gold today is used primarily for jewelry. But here's an example of a jewelry that I don't think many of you have ever seen before, a blue gold. A blue gold. Well, how do you get a blue gold? Well, it turns out you can make this gold blue by mixing gold with indium. That's another element, the periodic table, and you get these beautiful bluish blue gold materials. Gallium and indium both will do it, aluminum even make it bluish, but the indium is the best to get a very deep blue color. I've got a local jeweler in town who wants me to make it for him so that he can make a particular piece of jewelry which has a blue background and a red spot in the middle. Pretty easy. Here's an example of a use of gold. As I said before, you can cause the gold to be very thin by pounding it out, making it a very, very small layer. 1 ounce covers 1,000 square feet of glass. This is a building in Dallas. The light reflects from that gold beautifully. It keeps it much cooler as a result. Some of you don't like this picture, I'm sure, but some of you will be dentists someday, and you may have to deal with gold fillings, and some of you probably have gold in your mouth. So it's pretty important that we have quality bridges made out of gold, but even the Romans had bridges made out of gold. So this dentistry really goes back to a long time. This is before Rome was really strong. A few hundred years before that, the Etruscans were dominant. I was in Venice a couple of years ago, and I watched a glass maker take some gold pieces in a furnace and then melt them into glass and make chandeliers like this by dissolving that gold in a very thin foil into the glass. Beautiful chandeliers. Not cheap, but pretty. What's this from? Well, you can see from the slide. This is kind of important because it keeps the machine that goes up to Mars from the radiation that can come from outer space. It keeps the heat in also with a gold shield. So it's very important in our NASA program that we have gold. Electronics all have gold in them in various components, very thin wires, capable of being used in our various chips. But even in the nuclear industry, gold is used because gold-coated steel is used to break up the radioactive components of a steel rod. And they use these gold-coated components because of this. They last a long time in a very strong acid, like nitric acid. What is it that we study, though, as chemists? What is it about gold that we like? Well, one of the things I've enjoyed very much over the last 30 years is the fact that we've made some discoveries with regard to turning lights on with regard to gold. Gold compounds that under normal light might look like this, but putting UV light on these samples, they change color drastically, and in some cases glow very strongly. We brought along some samples later on. Some of you might like to look at some of these sorts of things, but it's an important discovery that relates to putting energy into these substances and then letting that energy out at a different frequency. Here's an example of some work that I did a few years ago with an undergraduate, a junior, where she made this compound and found out that the material under normal house light looks like this, but under UV light has a beautiful glow, very, very strong luminescence. Understanding why it was doing this was part of the work that we published with this particular student, Ramirez. A few years ago also, and published last year, we were able to discover that in fact gold compounds, which had gold interactions, could turn organic molecules into glowing species with light being emitted very strongly in the visible. So turning the lights on with organics is possible with these sorts of molecules. What do you use this for? Well, you can use it for sensing things. For example, this particular substance, a gold-thallium compound, is such that various types of vapors can go into the crystal structure of the material, and those vapors cause the gold compound to glow with different colors, depending upon the particular material going in. And so we can detect different materials readily. Chemistry itself can be a lot of fun. This is new work in our laboratory where we showed that we could produce compounds with very short gold-gold distances. These distances are some of the shortest that have ever been observed in gold chemistry, but they can become even shorter by reacting these materials with molecules like methyl iodide or with benzoyl peroxide or the halogens, and we get distances about 2.5 angstroms between the gold centers in these compounds. All new chemistry. We don't know some of the features of the chemistry themselves yet, but we're studying this right now in terms of what these materials can do and some of their properties. Recently, in work that I've been doing with Professor Wayne Goodman in our department, we've been looking at the oxidation of carbon monoxide on a titanium dioxide surface using a gold catalyst. Well, why would that be of value? Well, titanium dioxide is present in almost every paint that you have, every pigment. And so if you can put gold on small particles of titanium dioxide, then those titanium dioxide particles with gold on them will oxidize CO at room temperature. Well, what good is that? Think about it in terms of preventing carbon monoxide poisoning in a room, for example. If you painted your walls with these paints that contain this gold material, you might not have to worry about some of the hazardous things that have happened with space heaters of various sorts over the years. And what we've been learning is that it's a very, very small particle that does the actual oxidation. There's a cartoon of what possibly could be happening on the surface. The details are still being worked out. But this is what it looks like on the surface. We can look at these small gold particles. We start out with these sorts of materials and put them there, and so we've learned a lot about the composition of these components. But we're starting with molecules that I can have my students and my postdocs make in the laboratory. These sorts of materials. that we know the detailed structure of. Put those in a solvent, put them on the surface, react them with oxygen, and we get these particles that can convert CO to CO2 catalytically at room temperature. These catalysts are the best catalysts that have been observed for this process. And as you can see from this table, this particular catalyst, which was formed from a material in our laboratory, is about 3 times better than any catalyst that had been ever made before for the oxidation of carbon monoxide. Well, carbon monoxide is only one of many materials that we like to oxidize. We'd like to oxidize ethylene, for example, to an ethylene oxide. And in fact, the Dow Chemical Company has a process now using a gold catalyst to oxidize ethylene to ethylene oxide. Gold is also used in a lot of different ways by other chemists. Here's David Russell. David Russell has a research group that looks at mass spectroscopy of materials. And his group has found that using gold nanoparticles on a surface and hitting those particles with a laser where we have biomolecules also on that surface, the gold causes those biomolecules to fly. And so we can make these proteins fly. Huge molecules fly. And if we can make them fly as charged materials, then we can look at their mass. And so that can help us detect various proteins. And for medicine and analytical applications in medicine, it's a marvelous tool. Imaging. We're always interested in imaging of various sorts today. And gold is being used attached to various sorts of materials, usually through a sulfur center, for imaging all sorts of things. Imaging reactive sites that might involve a cancer cell. All sorts of various ways of utilizing these imaging capabilities. Why can you image gold? Because it's heavy, because it absorbs X-rays, because it, in fact, is easily seen by high energetic particles like that. Well, my own group has been very fortunate over the years. I've been working in gold chemistry almost 30 years in various sorts. A few years ago, a cover of Inorganic Chemistry, the journal that I publish in most often, had a picture of our work, and it was really a beautiful cartoon that was created by a postdoctoral at the department. And so it's given my research many years of interest in chemistry, with a lot of new structure types, a lot of new basic understanding of what's going on, and it's been great fun. It's also been great fun for me over the years to be an academic, where I've had a life that's led me to many interesting interactions. Not many of you have had a chance to drink a martini with an ex-president like I have, but someday you might get that chance. This was certainly a nice event for us a few years ago. But the most important thing for me, and I think all of us in the faculty, is you people, the students. That's what we're here for. And I'm glad you're here tonight. I'm glad you could be part of this activity. You're spread out. I'm glad I don't have a class that's spread out like you guys are, because I can't talk to you very well that way. But it is fun having students. But this poem is a poem that one of my postdocs a number of years found that is one that I really like very much. I wanted the gold, and I sought it. I scrabbled and mucked like a slave. Was it famine or scurvy? I fought it. I hurled my youth into a grave. I wanted the gold, I got it. Came out with a fortune last fall. Yet somehow life's not what I thought it, and somehow the gold isn't all. Thank you very much for being attentive. I certainly would be happy to answer any questions if you have some, but it's kind of hard in this auditorium. But raise your hand and holler if you do. And double points for my students. Yes?
What's the difference in the effect that gold has on animals?
The question was, what's the difference the effect gold has on animals compared with humans? We think that in the animals it's a skin disease that's like rheumatoid arthritis. And it probably behaves similarly to the situation with humans, but as a skin disease. Good question.